I want to present you today the Earth Survey Initiative, which is a European initiative heading for services on the big data, on the big raster data, and doing that in an agile way. That means ad hoc services allowing us to search at the moment the question pops up in our head and for whatever we want to do. Let's start from a standards-based perspective. I guess you're familiar with the Open Geospatial Consortium and standards like the Web Map Service, Web Coverage Service, Web Feature Service. So we have features that is a generic kind of object sitting somewhere in space-time. And then we have a special kind of feature, which is a coverage. We typically know that as an ortho image, satellite image, whatever, but there is more to it actually. First, it can be multidimensional, as you see here, satellite image time series or weather data, which can be 3 or 4 dimensional. There is still more though. We could have curvilinear grids, and we can have very strange grids up to general meshes, and all of that is a coverage as well. All they have in common is, typically, they are pretty big. Now, in ISO 19123 and in GML, we have a coverage which looks more or less like this. We have different grid coverage types, like rectified and non-rectified, referenced, non-referenced. So that's the standard grids we know. And then in addition, we have the multi-something coverages, which is point clouds, for example. That's multi-point coverages. We have trajectories, multi-curve coverages. We have multi-surface coverages, multi-solid coverage, etc. So in the end, it's going into the domain of geometric modeling. City GML, for example, is related to that. So we have a seamless integration. This is not replacing, this is not competing. It's just integrating all into one common schema. So all of that actually need support via web services. And all of that coming in n dimensions. 1, 2, 3, 4 dimensions. How should we encode that? Well, the definition actually in the standard is done in GML, so it's in XML. Don't you think that we need to encode that in GML? You just don't want to send a raster image in a GML format. It's way too big, of course. So we need ways to encode in other formats, and we have that in the coverage standard. First, you can do the whole thing in GML, of course, all the structure. If you say, hey, wait a moment, I want to send that in some other format, okay, do it. NetCDF, for example, which can host all these structures. Sometimes we will not be able to represent all structures. Okay, we lose some information, but that may be okay if we want to present it in a browser, just for viewing. If we still want to have the extra information, but use something like TIFF or PNG, you would put a header in there that contains the GML metadata. All these combinations are possible, and you can pick your favorite, and they all have a uniform, well-defined semantics. So that's something that is standard already in OGC. It's the, okay, hold your breath, GML 3.2.1 application schema for coverages. That's the official title of it. We call it GML Cov. So that's the big picture from our service side. We have seen the data structure. Now going into the well-known triad of feature data, coverage data, metadata, you find the pertaining standards in the world of OGC, let us say. We are located here with the WCS in the middle. And as you know, a web map service can display raster data, well, but it can only display. So that means it's for human consumption. You can look at an elevation model, but it's just a picture. You cannot put this into any other tool for further processing. A web coverage service gives you the original data unchanged and in a way that you can process them further. Like, for example, for terrain shading, for radio networks analysis and stuff like that. Actually, the web coverage service is something very simple. In its core, it just allows or supports subsetting. So you have some multidimensional coverage. The trimming allows you to extract something of the same dimension. Get a two-dimensional subset from a two-dimensional coverage. Get a 3D subset from a 3D coverage. Simple. The second option is slicing, where I reduce dimensionality by saying I want to have a two-dimensional slice from a 3D coverage or even a one-dimensional thread slice from a coverage. All that is in the core. It's a very simple functionality. Further extension standards define extra facets, like I want to extract bands from a satellite image. I want to do a reprojection into another coordinate system. I want to do scaling and all of that. There are different facets in a cloud or in a suite around the core standard. And then we have application profiles which define domain-oriented bundling, like for Earth observation, for meteorology, ocean, etc. So, if we want to bring that to the client, where's the problem actually with our data? Well, assume this is a climate simulation. How would a supercomputer produce the weather output? It simulates weather right now, that's 3D. Then, 20 minutes later, next slice of data written into a file. Then the supercomputer does the next 20 minutes, and so on. This is the way we store it. However, what we want to retrieve in the end is maybe give me the weather around Hanover for the last or next 200 years. So we do a slice orthogonal. That means the server has to read everything just to discard it, but for a few pixels. Extremely inefficient, of course. We do the same thing with our geotiffs. We get satellite images, and if we have a time series, we still store them slice by slice as they come in. Now the web coverage service allows an organization where we don't have to do it like this, but we can choose organizations which are much more efficient because they support different access patterns for ingest, data import, and for data export, so that we can balance this and can optimize it. And the server must find the best possible solution for this, and that's actually what we do in our research and in our product. And that gets me finally to the Earth server, which was the topic of the talk. In the end, Earth server is a European-funded initiative, 3 years. Now we have finished the first year. Almost 6 million, close to 6 million euro of budget. And the platform we use is rasdaman, standing for Raster Data Manager, and that is our multidimensional raster database system. If you visit our booth in the OSGeo Park, then we will gladly show you that in detail, what we can do with that. In the end, it allows you to do parallel queries on large multidimensional data, but not just like, for example, a grid infrastructure, hardwired, but we allow ad hoc queries. You phrase a query, I want to have the vegetation index, the snow index, I want to have a cloud mask, and it's sent on the fly. No extra products need to be maintained because it's done on the fly. Well, we apply this to 6 different use cases. Snow and ice modeling. EOX in Austria is doing this on ESA data, European Space Agency. NASA, the same thing on airborne data. MEO is a company in the north of Italy, in Ferrara, doing climate time series analysis. British Geological Survey, Plymouth Marine Laboratory, and as a special twist, we are looking at Mars geology. Ground-penetrating radar. On Mars, we can go down a few kilometers, and we want to find out whether, of course, there is water. Each of those is aiming at 100 terabyte, so we do queries against 100 terabyte databases, and then we want to do that distributed. If you want to have a coupling between atmosphere and ocean, you just send the query anywhere, and the atmospheric server will determine, oh, I don't have the ocean data, so I have to go there and ask for it. So distributed query processing, integrating data and metadata search. We can do on data now SQL-style search, ad hoc. And 3D clients is also something we are developing with the help of Fraunhofer Computer Graphics Institute in Darmstadt. I don't want to go so much into the technology. Show you one example that we have done earlier with a German remote sensing data center. We take a surface map, surface temperature in this case, extend this over time and have a 3D cube in the database. We allow queries in space and in time, and the result is a 3-dimensional cutout that we get. We, of course, can do slicing, horizontal. This is something that every system can do, but we also can drill through vertically. The gray one says, give me a temperature curve over Moscow for 1 year. Now this is interesting because what the client gets is about 1 kilobyte of data. Compare this to the about 10,000 images making up the cube on the server. So much faster because much better bandwidth utilization. Something you cannot extend easily. More CPU, not a big problem. More disk space, no problem. But bandwidth, that is something that is hard to crack. And by the way, it's just more convenient for the user if they get what they really want. That's the advantage of a query language that has been so successful in standard databases since the last 40 years. What you can do with such a processing services, time series analysis, image processing, signal processing, and hey, by the way, a web map service now just becomes a special kind of query. This is a screenshot of a 4-layer web map service picture generated through a database query. So with this distributed query processing, we can say we send a query, the difference between two NDVIs. Hey, but this server doesn't have the object. So what to do? The server will pass on subqueries to those nodes which hold the data. They process it, send intermediate results. They are integrated, and the client just gets a result. Doesn't see anything about this distributed and federated processing behind the curtain. That is what where substantial work has been done. Currently, we are integrating this into the standard version. So, in the end, we have raster data, which is a big part of the big data flood. I like to characterize this as sensor data, image, model, or statistics data. If you ask the petrol industry, they will tell you already today they have more bytes than barrels. So they are really in the flood of data. We have the OGC standards, which give you high-level access to this. And we use these OGC standards to internally optimize access so that we can have agile analytics in the end on really huge amounts of data, scaling into the petascale, into petabytes. And, excuse me, if you want to see more, then one URL is here, earthserver.eu, gives you some overview of the project. And if you want to see it just alive in color, let me kindly invite you again to come to our fair booth. That's rasdaman in the OSGeo Park. That already tells you that our rasdaman server is open source. And I will be glad to give you a demonstration or just discuss whatever comes to our mind. Thanks a lot for your attention.